All right, good morning, everyone. I hope you're all having a wonderful morning, even with the rain outside. I'm Kyle. I'm a senior production engineer at Meta, and today I want to talk to you about an incident that is near and dear to my heart. It is actually the most memorable incident of my career so far. Before we do that, though, I have a question I want to answer. What is a metastable failure? So straw poll, has anyone heard of the term before? All right, perfect. I see a couple of hands. That is actually more than I was expecting because the term was only somewhat recently popularized in a paper titled Metastable Failures in Distributed Systems at the Hot Topics in Operating Systems workshop in 2021, so just under 2 years ago. Now, in the paper, the authors listed 3 main attributes of metastable failures. The first is that there's a trigger that causes the system to enter a bad state, and the system will stay in the bad state even after the trigger is removed. The second attribute is, while the system is in the bad state, it's effectively unusable. And finally, there is a sustaining effect that prevents the system from self-recovering. So you might look at this and think, well, doesn't that just sound like cascading failure? And I would say, yes, you're right. But I want to argue that the two are actually distinct topics. Part of the criteria, remember, the third one, was that the system cannot self-recover. And I want to say that that implies that the system has the ability and the potential to self-recover, but just during a metastable failure, it doesn't. And that, I think, makes it distinct from a cascading failure. So I want to say that there are incidents that are metastable failures. There are incidents that are cascading failures. And you can have incidents that have both. There's no requirement that one is a subset of the other. And there is a lot of overlap, but again, I'm claiming they are distinct. So with that behind us, now that you know what metastable failure is, let's talk about my experience with the incident. So it was a bright and sunny morning on the East Coast, which was good because I was supposed to fly back to Seattle that afternoon. Now, the EU folk had scheduled what they call a DR peak load test, which is fancy language for we want to simulate our largest region failing at the time when we get the largest amount of traffic, peak. So all seemed well until, well, we started getting alerts flooding our CDN team channel. Now, I was on the East Coast. The on-call was on the West Coast, so I was 3 hours ahead. While he was getting woken up by pager duty, I started triaging the alarms. And it's like, okay, well, what's going on? Turns out we had one group of machines just disappear. Now, my immediate thought, when they were geographically correlated like that, we must be having a power incident in the data centers. So went, poked the machines. They seemed to still have power, but they weren't responding to ping. So I just started power cycling them. It's like, all right, this is our runbook. It sometimes happens. We don't like it too, but here's how we fix it. Contacted the web people. Hey, we got some funkiness going on. Please revert the DR test. And it's like, okay, no, we're all good. I'm going to continue packing for my flight. A few minutes later, I went back to my computer and it's like, all right, I can see the machines came back because I have ping output in my terminal, but why did it stop again? And it's like, this is kind of weird. I was focusing on getting machines back up. It's like, something is wrong here. The machines failed, came back healthy, and then failed again. Unfortunately, at this point, I was like, I got to get to the airport before I miss my flight. So I let the on-call know what had happened. I was like, yeah, you got woken up because of these alarms. Triaged it. It looks like something weird with the power. I've got to disappear for a bit. I'll check in later. So unfortunately, I'm going to talk about some of the intricacies of our CDN next, which means I should probably explain the architecture and some of the peculiarities of our CDN so you're not completely lost. Now, Meta uses a CDN pretty much like anyone else in the sense that we use it to cache content physically closer to people. Now, this makes the experience for people who live further away from our data centers a lot better because the speed of light is less of a factor in the latency. Mainly because, well, bits don't physically have to travel as far. So, like Kurt said, I'm going to use photos of my dog as examples for the media that gets stored in the CDN. So I did say that we are a fairly standard CDN, but we do have unique points. So one of the big ones is that we store at least 2 copies of the photos and videos that you upload. Whatever you upload goes to one region first, and then gets replicated to another region. We do this so we're durable against region failure. Like I said, we had scheduled a DR peak load test to simulate one region failing and just going offline. Earthquake, fire, network outage, doesn't matter, we just assume it's gone. And we want to say, yes, we will still be up even if that happens. So this means that, well, media gets spread all across. Completely random, there's no uniform nature to it whatsoever. Now, in this example, my media gets kind of scattered a bit like this. You can see there's 2 copies and it's just shuffled around the regions. So the question now is, all right, this photo has ended up in my friend's Facebook feed. How does the system know which region to go and fetch the photo from? Now, for efficiency, we don't want to say, okay, well, we have the region pair stored. We'll just arbitrarily say the first region in the region pair is going to be the primary, second one is secondary. Send all traffic to primary until it fails and then fall over to the secondary. That's not exactly efficient because you're going to get a lot of idle capacity in the secondary. So what we did was we introduced region weights. This is roughly the sum of the web server capacity in each region. Now, it's a global thing. The entire system has this single unified view of this is what each region's weight is. But it is actually a bit of a lie, because remember, I said media is only stored in 2 regions. So the routing ring for my photo kind of looks a bit like this. Only 2 regions are possible, so the actual region ring looks like this. It collapses down to just these 2, and the system makes a random selection from this ring. And of course, you might be wondering, okay, well, how do you actually respond to a region failure? Because that seems like you're not single point of failure, but you've kind of collapsed it down. The trick here is that the system health checks each of the regions continuously. When it detects a failure, it actually drops the failing region from the routing ring. This has the effect of forcing all the connections or all the requests for a particular region pair to go to the other region that has not failed. So crucially, though, this health check and the decision to drop a region is a local one. It is made by each POP independently. This contrasts to the region weights, which were a global thing, where the view was essentially common across everything. You also might be wondering, I mentioned the term POP, but didn't explain it. Here's the part where I explain it. So the request flow functions like this. My friend is on his phone, he's scrolling through his Facebook feed, lands on this photo of my dog. His browser will go and make a request to his nearest POP, point of presence. This is the thing that caches all the photos and videos. There are many of them, but in this example, I'm just using one. So in the POP, our system says, okay, well, got a request for this media. It's not cached, so I need to go back to the region. It goes through the region selection flow, sends a request to the region. In the region, there's a load balancer that randomly selects a web server. The web server goes and fetches my photo from storage. The web server then says, okay, actually, dude's on a phone. We need to make the photo smaller. It sends the photo over to a transcoder. The transcoder resizes the image, sends that image back to the web server. Web server then sends it back to the POP. The POP caches the image and then forwards it on to my friend. So at this point, we can go back to the story. Assume I've made it to the airport. I'm through security at this time. I'm sitting down at the gate. I pull out my laptop. I get back on BlueJeans to see where we are. And so a quick recap. When I left, machines were in a cycle of failing, coming back to healthy after power cycling, and then failing again. In the time I was on the bus, well, we found out more than one region was impacted. And because more than one region was impacted, we were like, could this be a cascading failure? That's not great. Now remember what I just mentioned about the region selection. particularly the health check part. What we were seeing was waves of requests go between regions. As one region went unhealthy, the pops independently fell over to the next region in the region pair. That region got overloaded, and we fell back to the first region, which had, in the meantime, become healthy again. So that led us to thinking, like, okay, this sounds like a cascading failure. And you might be wondering, like, isn't the title of the talk Metastable failure? So I want to say, yes, this actually is a metastable failure, because all three of our criteria were met. The DR test was reverted. That was the trigger for the failure, and we removed it. But we were still failing a lot of requests. The system isn't really usable. And finally, well, regions would get hit by a thundering herd whenever they individually recovered, which, hello, sustaining effect. So at this point, we had thought, okay, well, cascading failure, we roughly know how to fix this. Let's get started. Physical recovery was actually already ongoing. Remember, I started by power cycling machines. Turns out, though, it didn't really do too much. What had actually happened was not a power incident, but that some machines had ran out of memory and crashed. So what we ended up doing or figuring out was the thundering herd on region recovery would come back in when the region was up and take the machines which we had freshly recovered right back down. So we're like, okay, physical recovery, clearly not enough. Let's move on to classical remediation for cascading failures, load shedding. So we did stuff like tightening our rate limits, changing our firewall to like drop more connections, reducing the load on each individual machine so there's less chance of an overload. We did other things like disabling background content fetching in applications. So you don't have photos in Messenger download automatically, for example. That was a way to reduce the number of requests. And we also tried adding additional web servers. Now, none of this was instant, so this was all taking some time to actually make the change and then see if it worked. And that led to the title of this talk, We're Still Down. We actually got to the point of preparing to turn the CDN off completely, blocking all incoming connections so we could let the region stabilize and only then let connections back in, when someone actually had an idea. You know, these health checks are causing a lot of problems. What if we just change the health checks to ignore reality? And this was the unorthodox bit that we actually did. We disabled the health checks completely. So the load balancers in the region lied. It's like, no, sure, that machine might be down, but no, we're going to send traffic to it anyway. On the POP side, yeah, that region might be failing connections, but we're just going to trust that it will accept something. We'll send the connections there. And the remarkable thing is, we actually saw recovery. Machines that were unhealthy became healthy. Machines that we power cycled came back and stayed up. So you're probably wondering, like, that doesn't really make sense. You disabled health checks, and an unhealthy machine, an unhealthy system got healthy. Kind of confusing, right? It's not intuitive. The thing here is that what we needed to do was we needed to spread the load wide enough so that individual hosts did not get overloaded. We didn't care if individual machines are up or shedding load or had crashed. We just needed to get the average request per machine down. And here's the key bit. Not average request per healthy machine, average request per machine. So disabling the health check forced the connections to be spread across the machines. We're treating all the machines as up. So this meant we weren't lasering the healthy instances out of existence. Here, have more requests than you can handle because you're healthy. There was no thundering herd of traffic because we were forcing a normal traffic distribution. The POPs were connecting as expected across all the regions. So this had the effect of breaking the sustaining effect within the metastable failure, and it allowed us to move back towards a normal operational state. So this is not an unknown technique. So there's at least one article about it, and this is a quote from the article that I found, titled How to Avoid Cascading Failures in Distributed Systems by Laura Nolan. Now, Laura's actually at the conference, so you might be able to run into her later. But her quote was, "Many load balancing systems use a health check to send requests only to healthy instances, though you might need to turn that behavior off during an incident. to avoid focusing all the load on brand new instances as they are brought up. And this is actually one of the reasons I'm giving a talk today. This incident was hard. It was nerve-wracking to say that, hey, we're the experts on the system. We designed it, we built it, we run it. We're the cavalry if stuff goes wrong. Something went wrong, and we're stuck. We were hours into this incident, and we only recovered because someone had the idea, all right, we should actually disable health checks. So why I'm talking today is to let you all know that, hey, this is actually a reasonable way to recover from cascading failure. So now you can all go back. If you're met with a similar situation, hopefully you can remember, like, oh yeah, you know, there was that one weird trick, and remember this. So our incident is mitigated. I got on a flight hours later than I was supposed to. And now it's time to understand what happened, why it occurred. So we're going to go back to our CDN request flow, because one particular component did something kind of silly. The transcoder tier was overloaded. And one of the protections is that it can send requests cross-region instead of failing the requests completely. Unfortunately, by default, when we do a cross-region request, everything in the request is compressed. Why? Because cross-region bandwidth is more expensive and we have less of it. So in isolation, good ideas. But the problem is we're about to compress uncompressible content. So the web servers end up using more CPU to compress the bytes that were sent to the transcoder. We had some machines start to run out of memory and crash because it turns out the CPU couldn't send bytes fast enough out to either the transcoder or back to the user. Then bytes were coming in from the storage service. So we also had some machines kick in its own overload protection because we did have that configured, but they also shed all new connections, including health checks. So they marked themselves as unhealthy. This meant that once that region had reached the threshold of failed health checks, remember, our POPs fail, when our health checks fail, they remove the region from the routing ring and concentrate all the traffic on the other one. So we ended up in a situation where traffic was overloading one region, failing that region, falling over to the second region, and just repeating back and forth, traffic sloshing around the world. So now we knew what had happened, and we knew roughly why it had happened. I'm going to talk and explain what we changed to avoid it from happening in the future, but first I want to talk about some things which we had found during the incident to have hindered us or helped us. So first of all, we had a delayed realization of the incident scale. Remember, when I started, it was like, oh, okay, well, we've got a particular region down. We've got machines in a particular region down. Must be a power failure. Let's get the machines back up. This ended up with people joining the incident call, not because they were paged, but because they had woken up, gone on Facebook, and was like, my photos and videos aren't loading, but everything else is. Something's wrong. Let me reach out to the on-call. Oh, there's an incident. I better join. The second thing was we had two distinct failure modes. The first was that machines were outright crashing. And the second was that they were just simply going unhealthy. They were still running the web service, but it was just, yeah, I'm not healthy, I'm not happy. And we ignored that in favor of, let's get the machines back up. The third thing was that health checks were affected by the load shedding, causing traffic oscillations both between regions and within the region itself. But thankfully, well, we had two things that made this incident a lot less worse than it was. The first was that the CDN read path was the only thing that was affected. The CDN write path was entirely functioning perfectly fine, so we had no data loss during this incident. The second thing was that the POPs continued to serve stale cached content. So I mentioned we're going to talk about design changes. This is that part. So it's unlikely that this specific incident would happen again because we did things like, oh, let's not enable compression on the transcoder tier. And that would have been enough to stop this incident from happening in the first place. The thing was, though, we kind of revealed that, hey, you know, it's dangerous. There's quite a few ways to get into this metastable failure state where we start sloshing traffic around. How can we prevent that? And those are the design changes which I'm going to talk about. So the first is that we made an explicit choice to say, when we have a count of machines below the healthy threshold, spread traffic evenly across all machines instead of overloading the remaining machines. Or simply, pretend everything is fine. Thankfully, if you're using Envoy, this is supported by default. The term you are looking for in your configuration is panic threshold. If you're using the AWS application or network load balancer, you have something similar. You're going to be looking for target group health, unhealthy state actions. We did a few more things to our health checks. Another one is that we changed it to look at the short-term history, not only the most recent check. We did this to try and delay the unhealthy to healthy transition, so we stopped that oscillation. We also prevented the health checks from being subject to load shedding within the web server. Now, this is actually kind of dangerous because the health check handler must be lightweight. If something ends up hammering this health check endpoint, a DDoS attack, for example, you will cause a denial of service that the web server can't shed by design because you've told it, do not ever shed these requests. Or if someone adds a new feature that ends up making the health check code path a lot heavier, well, you're going to have these requests build up and end up starving other requests of any web server capacity. So the AWS Builders Library actually has an article that I found particularly enlightening entitled, Using Load Shedding to Avoid Overload. And it actually calls out this particular point about needing to prioritize health checks, saying the most important request that a server will receive is a ping request from a load balancer. Now, I read that article well after the incident in question had happened, but just reading that, I was like, yeah, that would have helped. So we also changed the CDN design. Remember how we were routing traffic to regions just based on the routing weight? We went back and adjusted the weights so that in a future DR scenario, we don't have situations where a region would take more than 2 times the normal amount of traffic. So this was in part because it was very difficult to actually think about, okay, well, what happens in a DR scenario? What do we expect the traffic increase to be? The second thing that we changed, also with the weights, was we did a periodic automated recalculation of them. And we changed it so that it's not just based on the number of web servers that we have, but also how much storage capacity that we had. Because one of the things that we found out was the first region that failed had actually had more storage added to it, but we never increased the web server count. So it was naturally getting more requests than we expected, even during steady state operation. So there's also kind of a grab bag of things that don't really fall under any particular section. So we have automation built to support tier isolation. So now we have a clean separation between internal CDN use cases and external CDN use cases. We invested a bit more in stronger container level isolation and resource limits, cgroups v2. So we don't have situations where a misbehaving service takes down the entire machine. We just take down the container itself. And finally, we were also at the early stages of adding autoscaling to parts of the system. So we just effectively stepped on the gas for that and said, can we get this done in the next month, please? We added autoscaling to both the transcoder and web servers. So, wrapping up, takeaways. First is that metastable failures are a class of failures. They occur when a system fails under an increase in load and can't recover due to a sustaining effect. The second takeaway is that you can load shed by disabling health checks and forcing a normal traffic spread. And the third and final thing is that please spread traffic across all your services if there's a large percentage of failures, so you avoid overloading the surviving services and you avoid causing a cascading failure. I recommend looking at the behavior of your own system to understand what will happen. I've mentioned resources for both Envoy and AWS ALB and NLB. So with that, questions. It's like, as a reward for any questions, every time I get a question, I'll advance a slide and show you a photo of my dog.